Space has always been fascinating to people as they observe the sky. Scientists and philosophers alike have pondered life's deepest questions. What would it be like to go to distant galaxies and, more importantly, what kind of life might exist there? Space is just space. Its size is absurd. It would take years to reach our nearest neighboring star, even if we could travel at the limiting speed of the universe. At least we have science fiction like Star Trek to test the human imagination, although we have not yet found the answers to these problems. But today, thanks to NASA's warning system, the final limit could be within reach. Since nothing can move faster than the speed of light, this is the fastest it has ever been. Light can reach the moon from Earth in just over a second due to its speed of 300,000 kilometers per second. In less than the blink of an eye, light can travel from Los Angeles to New York. Proxima Centauri is the closest star to Earth, separated by 4.25 light-years. The Parker Solar Probe, which is currently in orbit, is the fastest spacecraft and reaches a maximum speed of 450,000 meters per hour. At that speed, you could get from Los Angeles to New York City in just 20 seconds, but the solar probe would need about 6,633 years to reach Earth's nearest neighboring solar system. Why can't we use conventional rockets? Conventional rockets are ineffective because they are too slow to travel between stars. The distances in space are enormous, and conventional rockets cannot reach speeds high enough for practical interstellar travel. Spacecraft, such as the Space Shuttles and Voyager probes, are limited by their current speed, which is very slow compared to what is required to reach other stars. Even the New Horizons probe, which traveled to Pluto, would take tens of thousands of years to reach the Alpha Centauri system if it were pointed in that direction. Faster than light travel, which would be necessary for convenient interstellar travel, is currently only possible in science fiction with concepts like wormholes and warp drive technology. Star Trek writers ran into problems developing the series due to its space opera nature. They wanted to avoid making the series boring or conventional, so they needed to find a dramatic way to transport the characters through the universe while still maintaining some fidelity to physics. The biggest challenge was the enormous distance between galaxies, which even at the speed of light would take hundreds or thousands of years to travel. The solution came with the introduction of warp velocity, which allowed faster than light travel. To justify this, Newton's third law of motion was used, which states that there is an equal and opposite reaction to every action. This law explained how a ship could move at such extreme speeds. When you accelerate in a car or fly in an airplane, you experience Newton's third law of motion. You feel pressure on your seat as the vehicle moves and pushes you against the seat. This is similar to what happens on the Star Trek Starship Enterprise. However, if the ship were traveling at near light speed, the people on board would be crushed due to the difference in mass between them and the ship. To solve this problem, we turn to Einstein's theories about space and time, which allow us to overcome the limitations of the speed of light. According to Einstein, the speed of light is constant for all observers, and time is relative, meaning it slows down as you approach the speed of light. This has been demonstrated by experiments with atomic clocks on fast rockets. For the crew of the Enterprise, time would pass more slowly, allowing them to travel cosmic distances in a reasonable amount of time. However, they still face the challenge of staying in sync with Federation time to manage an interplanetary civilization. The ship needs to travel faster than light to be efficient in its space travel. According to Einstein's special theory of relativity, traveling faster than light is not possible. However, the general theory of relativity provides us with a different perspective. In this theory, space and time can be influenced by gravity and distorted. If we could control space-time and create curvature, we could avoid the need to travel at the speed of light. The Enterprise in Star Trek uses a warp drive that generates a warp bubble around the ship. This allows the ship to move locally at modest speeds while warping space-time, maintaining synchronization between its starting point and destination. Although in our current reality we cannot curve space and time, in the fictional world of Star Trek, This technology is possible through the use of a compound called dilithium and a curvature engine. The ship and its crew are protected by this curvature bubble as they navigate through space. In 1994, physicist Miguel Alcubierre proposed the idea of compressing spacetime in front of a spacecraft and expanding it behind it, which would allow travel at speeds faster than light without violating the rules of relativity. However, this theory has an important limitation. It requires negative energy or mass. Negative mass is hypothetical and has not been observed, so the only option would be negative energy. For a warp drive to work, a massive amount of negative energy would be needed. Alcubierre estimated that it would require the mass of the entire observable universe to create a 100-meter bubble using its curvature engine. Subsequently, scientist Chris Van Den Broek demonstrated in 1999 that it would be possible to reduce energy requirements dramatically by increasing the volume inside the bubble, while maintaining a constant surface area, but it would still be much more than is feasible with our current technology. In recent research, methods have been proposed that could bring warp engines closer to reality in a futuristic environment. Additionally, NASA engineer David Burns has developed a design for an engine that he claims could reach speeds of up to 99% of the speed of light without using fuel. Burns uses a thought experiment with a box, a weight, and springs to demonstrate his idea. Although there are limitations due to the principle of conservation of momentum and special relativity, there is a possibility of achieving momentum using ions instead of a moving weight. These advances demonstrate the potential for human ingenuity to overcome seemingly insurmountable obstacles in the future. The Burns helical motor is an expanded spring-shaped design that accelerates ions in a loop to produce thrust. Although the idea is impressive, it presents significant practical challenges. The helical design would require a considerable size of 656 feet long and 40 feet in diameter, and a large amount of energy would be needed to achieve significant thrust. Although the process is inefficient, in the vacuum of space it could work if enough time and energy is available. Although not everyone shares Burns' vision, there are many people interested in traveling to other stars. Although achieving this goal may be difficult, ignoring all options guarantees that it will be impossible. As the saying goes, 100% of the shots that are not attempted are missed. David Burns' helical engine is a major advance in space exploration. Although it is mainly theoretical and faces practical challenges, it could be crucial in unlocking the secrets of the universe and opening up new possibilities for exploration. Although we do not have the detailed plans to build a functional engine at present, the future remains promising. Creativity and perseverance will allow us to continue pushing the limits of space flight and discover new frontiers. Wormholes, taking shortcuts through space. Wormholes, theoretical shortcuts that connect distant regions of the universe, are postulated on the cosmic highway. These tunnels could allow interstellar and intergalactic travel without exceeding the speed of light. Wormholes would arise from the curvature of spacetime according to the equations of general relativity. These holes would be like bridges in the fourth dimension, connecting points in three-dimensional space. Although from our perspective it would seem like an instantaneous jump, in spacetime it would not exceed the speed of light. However, the stability of wormholes presents problems. The natural ones would be unstable and would collapse quickly. Keeping a wormhole open would require exotic matter with unusual properties, the existence of which is not yet proven. Creating a wormhole would require manipulating singularities and dealing with quantum gravity, not yet fully understood. Navigating through them would also be a challenge, as they could lead to very different places or times and even different universes if multiple universes exist. There are risks when traversing a wormhole, such as the possibility of feedback and destruction of the hole and objects passing through it. Despite the challenges, research into wormholes continues, as they offer fascinating travel possibilities and the opportunity to unite general relativity with quantum mechanics, which would help us better understand the universe as a whole. Quantum entanglement. Quantum entanglement is an intriguing phenomenon in quantum mechanics that allows for an instantaneous connection between particles, regardless of the distance between them. Although it appears to defy the speed of light, its use for faster travel or communication faces significant obstacles. Quantum entanglement was verified experimentally and is an established part of quantum theory. Although the possibility of using entanglement for instantaneous communication or quantum teleportation has been raised, there are important limitations. First, entanglement does not allow classical information transfer, since entangled quantum states are not readable until they are measured, and the results appear random. Second, measuring or manipulating a quantum system typically collapses entanglement, making it difficult to maintain over long distances. Finally, the non-communication theorem in quantum mechanics states that it is impossible to transmit classical information through a quantum channel alone. Although quantum entanglement has applications in quantum computing and cryptography, its usefulness for faster-than-light travel or communication is highly unlikely based on our current understanding. Although fascinating for understanding the quantum world, its practical application in this regard faces insurmountable challenges. The hypothetical tachyons. Tachyons are hypothetical particles that could travel faster than light. Its name comes from the Greek word tachys, which means fast. According to special relativity and quantum field theory, tachyons have peculiar properties. Unlike normal particles called bradyons, which would require infinite energy to reach the speed of light, tachyons would require infinite energy to slow down to the speed of light. This is because an imaginary or negative mass is attributed to them. Tachyons have opposite behaviors to normal particles. They speed up when they lose energy, and seem to experience time in reverse from our perspective. However, its existence raises complications and paradoxes, such as the violation of causality. Although evidence of tachyons has been searched for decades, none have been found. The phenomena attributed to them in the past turned out to be experimental errors. Its appearance in a theory usually indicates instability. In short, tachyons are speculative, and there is no consensus on their existence among physicists. Based on our current understanding of the laws of physics, faster-than-light particles are unlikely to exist. However, if the opposite were proven in the future, it would require fundamental changes to our current theories. Negative energy as fuel for faster-than-light travel. Negative energy, an intriguing concept from quantum physics and general relativity, could be the key to faster-than-light travel. Although negative energy does not exist in classical physics, in quantum mechanics it is allowed under certain conditions. An example of negative energy is the Casimir effect, where two uncharged metal plates experience an attractive force due to the presence of negative energy between them in a vacuum. Negative energy is applied in faster-than-light travel, such as warp drives and wormholes. The Alcubierre drive, for example, uses negative energy to create a bubble of warped spacetime and move at superluminal speeds. However, the use of negative energy presents significant challenges. Firstly, the production and stabilization of a significant amount of negative energy in the long term is currently unattainable. Furthermore, its existence raises concerns about the violation of fundamental energy conditions and the possibility of paradoxical effects, such as time travel or the creation of perpetual motion machines. Furthermore, the principle of quantum interest suggests that accumulating negative energy leads to the generation of massive pulses of positive energy, nullifying the desired effect. Despite these challenges, research on negative energy continues to inspire scientists. Although we do not yet fully understand its nature, its study could have a revolutionary impact on space travel and energy production. Defeating the light through time travel. Time travel involves moving through time rather than faster than the speed of light. According to Einstein, time and space are intertwined in space-time. Gravity bends space-time and affects the trajectory of objects and the flow of time. Traveling to the future would theoretically be possible by approaching the speed of light or massive objects, slowing down time for the traveler. However, traveling to the past is more complex and would require sharp time curves. Some solutions to Einstein's equations suggest the possibility of travel into the past, but these solutions are specific and require particular conditions. Furthermore, travel to the past presents problems such as violations of causality and paradoxes. Some physicists propose that quantum mechanics and Novikov's self-consistency principle could avoid these paradoxes, but this is speculative and many physicists are skeptical. A theory of quantum gravity is expected to provide clearer answers about the feasibility of time travel. The concept of time travel raises fascinating questions about reality, causality, and the nature of time from a scientific and philosophical perspective. But for as long as we have been studying the science and history of our universe, the Big Bang has been the explanation for everything. There have been hundreds of studies and thousands of scientists who have worked on the research, and according to the data, the Big Bang has been the leading theory explaining how the universe formed. Dark energy was believed to be the largest energy source, even larger than galaxies. Dark energy is the anti-gravitational force that creates the expansion of the universe. But science today is very different from what it was before, and with technological improvements come new theories. We often realize that things we believe to be 100% true are far from being true. Well, that just happened again. The images captured by the James Webb Telescope of new galaxies are impressive, but for scientists, they are surprising and challenging. These galaxies are smaller, softer, older and more numerous than expected, causing panic among them. These images directly contradict the Big Bang hypothesis, which has been considered an unquestionable truth. The galaxies observed are much smaller than expected for an expanding universe, and their softness and age also defy expectations. Furthermore, the number of galaxies observed is much larger than predicted, raising questions about the accuracy of the Big Bang hypothesis. According to the Big Bang theory, at the beginning of the universe, all the matter, energy and fundamental blocks of the cosmos were compressed into an extremely small and dense point, called a singularity. The infinite density within the singularity implied an enormous amount of mass and energy concentrated in a tiny space. The universe subsequently underwent expansion and inflation for approximately 13.7 billion years, leading to the formation of galaxies, stars, and other cosmic structures. Cosmic inflation played a key role in smoothing out irregularities, homogenizing the distribution of matter and energy, and setting the stage for the evolution of the universe as we know it today. As the universe expanded, its expansion rate slowed, but it still continued to expand measurably, known as cosmic expansion. This expansion has been observed through the redshift of light from distant galaxies. During this process, since the Big Bang, the universe underwent transformations and nucleosynthesis, the creation of light elements such as hydrogen and helium. These elements laid the foundation for the formation of stars, galaxies, and more complex cosmic structures. The existence of cosmic background radiation, CMB, is significant evidence of the Big Bang theory, as it aligns with its predictions and supports the idea that the universe was in a hot, dense state before its expansion. Taken together, this evidence provides strong support for the Big Bang theory. Cosmic background radiation, CMB, offers us a window into the beginnings of the universe, confirming the Big Bang theory as the most accurate explanation of its origins. Several lines of evidence support this theory, such as the redshift in distant galaxies, which shows the continued expansion of the universe. Furthermore, the abundance of light elements and the distribution of large-scale galaxies also agree with Big Bang predictions. The gravitational force has been essential in shaping the distribution of matter and the formation of galaxies, and the filamentary and network structure we observe aligns with the gravitational effects predicted by theory. Together, this evidence supports the idea that the universe began in a hot, dense state and has evolved through expansion over billions of years. Images from the James Webb Space Telescope challenge what Big Bang theorists thought about the growth of galaxies. Small galaxies were expected to evolve into larger galaxies through collisions and mergers, but observations show smooth, well-organized galaxies, calling into question the frequency of these processes. This suggests that galaxies were never small to begin with. Furthermore, the optical illusion predicted by the expansion of the universe, where objects appear smaller with distance, has not been found. As for stars, their color can help determine their age since their lifetime is related to the amount of fuel they burn. The James Webb Space Telescope has observed distant galaxies that appear to be older than expected according to the Big Bang theory. Some of these galaxies show stellar populations more than 1 billion years old, which contradicts the idea that nothing should have existed before the Big Bang itself. Additionally, James Webb images have revealed a large number of massive galaxies, challenging the premise that the number of galaxies would decrease with distance in the past. These findings call into question the plausibility of the Big Bang theory. It is interesting to note that the Big Bang theory presents 16 incorrect predictions in the scientific literature, which is significant. For example, the estimate of the abundance of helium and lithium is higher than expected, and there are unexplained phenomena, such as the absence of the expected illusion of the size of objects as the distance increases. Despite these contradictions, criticism of the theory has not been widely disseminated in the media, possibly due to resistance from certain groups and dependence on funding for cosmology research from sources controlled by supporters of the Big Bang theory. This situation can make it difficult to obtain funding for alternative research and hinder scientific progress in exploring other theories. Years ago, if researchers could fund their own cosmology research as a side pursuit, they still had the opportunity to publish heretical papers. However, the system also blocked them. These documents were often ignored by the established cosmological community. As the crisis within the field of cosmology became evident in 2019, the cosmological establishment rallied to protect the failed Big Bang theory through censorship, as it lacks alternative defenses. It has now become extremely difficult to publish papers that are critical of the Big Bang theory in astronomical journals. Even if someone wrote a document, it would likely never see the light of day. This brings us to a crossroads point. If the Big Bang theory is not really accurate, how could the universe have formed? Surprisingly, there are some theories that could explain it all. The steady-state theory is one of the most popular, and proposes an alternative explanation for the nature and origin of the universe. According to this theory, the universe is in a perpetual and unchanging state, meaning that it has always existed and will continue to exist indefinitely. Unlike the Big Bang theory, which suggests a point at which the universe began, the steady-state theory suggests it has always been there. One of the key aspects of this theory is the concept of continuous creation, which proposes that matter is constantly being created throughout the universe to compensate for the apparent expansion of space. In other words, as galaxies and other celestial objects move away from each other, new matter is continually generated to fill the empty spaces and maintain a consistent matter density in the universe. This idea of continuous creation serves as a way to explain the observed expansion of the universe without the need for a singular event like the Big Bang. Another theory is eternal inflationism, which introduces the idea that our universe is just one component within a much larger multiverse. According to this theory, the multiverse consists of numerous bubbles of universes, each with its own unique set of physical laws and properties. These universal bubbles exist alongside one another, occupying separate regions within the broader multiverse. The key feature of the theory of eternal inflationism is inflation, which refers to the rapid expansion of the universe that is believed to have occurred shortly after the Big Bang. In this theory, inflation is not a single event limited to the initial stages of our universe's existence, but rather an ongoing process that continues to take place in specific regions of the multiverse. During periods of inflation, certain regions within the multiverse experience rapid, exponential expansion, leading to the creation of new universal bubbles within those regions. Each newly formed universe within the multiverse possesses its own distinct physical laws, constants, and properties, resulting in a vast collection of diverse universes. There is also the cyclical universe model, which proposes a pattern in which the universe goes through a series of repetitive cycles. Each cycle begins with a Big Bang, a tremendous explosion that marks the birth of a new universe, and concludes with a big crunch, a dramatic collapse where the universe contracts back into a highly dense and hot state. In this model, the universe goes through an expansion phase after the initial Big Bang. During this expansion, galaxies, stars, and other cosmic structures form, and the universe gradually becomes larger and less dense. But the expansion eventually slows and reverses due to the force of gravity exerted by matter and energy in the universe. As the expansion slows, the universe enters a phase of contraction known as the Big Crunch. During this phase, the universe becomes increasingly compressed and denser, leading to a highly compact state. Ultimately, all matter and energy in the universe is concentrated in a singularity, a point of infinite density and temperature. After the Big Crunch, a new cycle begins with another Big Bang, and the process repeats itself, leading to an eternal cycle of expansion, contraction, and rebirth. These theories offer interesting explanations for the existence of multiple universes and the remarkable diversity observed in our own universe. Could this be the definitive proof we need to debunk the Big Bang theory? Let us know which side of the argument you stand on in the comments below. If you liked this video, give it a thumbs up, and as always, we'll see you in the next one.